So chemical bonding questions, just 1 second. It's this one. So about sigma bonds, sp3 hybridization, sp2, sp hybridization, and we were going to talk about the shapes of molecules. So this part over here. Okay, this is what we were dealing with. So we did the first question, I think. We did the first question. We're going to start with the second question. The second question is that which elements can form pi bonds? So just a quick brief recap of what pi bonding was. Pi bonding is when you have a double bond. I told you that whenever there's a single bond, that's a sigma bond. The first bond between atoms is always a sigma bond. This is what we did. So whenever you have a single bond, that is sigma. Whenever you have a double bond, that's one sigma and one pi bond. And if you have a triple bond, the first one is a sigma and the other two bonds are pi bonds. So for example, in an oxygen molecule, oxygen needs to fill up 2 of its orbitals. So this oxygen atom over here has an electron in one of the orbital and an electron in this orbital over here. This oxygen over here also has 2py and 2pz orbitals are empty, so they need 1 electron each. So there's an electron over here and an electron over here. So the first overlapping that happens, both atoms try to pull each other's electrons. So the first overlapping that happens in the middle, and that's your sigma bond. So the electron density is right in the middle, and that's your sigma bond. The other orbitals then are parallel to each other, and they then start overlapping above and below. They both try to pull each other's electrons, and they end up forming a pi bond. So the second bond between atoms is always a pi bond. And the same was the case for triple bonds. We talked about triple bonds. We talked about nitrogen atoms. Nitrogen had to fill up 3 of its electrons. So there was a p orbital, another p orbital on the z-axis, on the y-axis, and there's a green p orbital on the z-axis. So the first 2 p orbitals, they started overlapping and the electron density was right in the middle. Then the other 2 p orbitals were parallel to each other, the blue ones, and they started overlapping above and below. They ended up forming a pi bond. And then the green ones were also perpendicular to they were on the z-axis, so they started overlapping in front and behind. So the first bond that was formed, the first overlapping happened in the middle. That was your sigma bond. So coming back to the question, which elements can form pi bonds? So any element that's capable of forming a double bond, that would form a pi bond. So carbon is capable of forming a double bond. For example, it's in ethene, it does form a double bond. So the middle one is basically a pi bond. And we did do ethene's structure as well. In ethene case, carbon was sp2 hybridized. 3 of its electrons were busy making bonds. Carbon was only bonded to 3 atoms. This carbon was also bonded to 3 atoms. And carbon's 4th electron initially remained unchanged. And that 4th electron ended up overlapping above and below. So there was overlapping that was happening above and below. They ended up forming a pi bond. So the first bond was a sigma bond. The double bond came when there was a pi bond that was formed. Oxygen can also form double bonds. Anything that can form double bonds, that would form a pi bond. Nitrogen can form a triple bond. It can form 2 pi bonds. So is this clear? Is this clear to everyone? Anna, Amna, is this clear? Alicia, Isa, is this clear?
Yes, sir. Yes, sir.
So now we've got the diagram shows 2 different compounds, and if you can see clearly, the 2 compounds, what is the total number of structural isomers, including, forget the structure isomers, let's do the second part. What's the number of pi electrons? So whenever there's a double bond, that's one pi bond. So that means if you see a double bond, that means there's an orbital overlap that's happening like this. I mean, the first bond was right in the middle. I mean, the electrons were shared right in the middle. The second bond came when the overlap happened above and below. So that's a pi bond. A pi bond is basically just like any bond that has two electrons. So that's two electrons being shared. There's a pi bond over here as well. So that means the two carbon atoms over here. Remember, or maybe some of you haven't studied this. Just remember that each point on the structure is a carbon atom. So they would form a pi bond as well. So that's another double bond. So that's another pi bond. So that's two electrons. The second one also has a pi bond over here. So that's two electrons. And there's pi bond over here. That's another two electrons. So the total number of pi electrons in both cases, that's 4. Next is nitrogen exists in air as covalently bonded diatomic molecules, which features are present in one N2 molecule. Now, N2 has a triple bond. So that means it's one sigma bond. The first overlap is right in the middle. The other two, one is going to be above and below. Then there's going to be an overlap in front and behind. We did draw this one. It's basically this one. It's got 3 orbitals that needed filling up. So the first electrons, they got shared in the middle. Then an overlap happened above and below, and an overlap happened in front and behind. So whenever you have a triple bond, that's 1 sigma and 2 pi bonds. So going back to the question, it's saying it's got 3 pi bonds. That's wrong, because whenever you have a triple bond, that's 1 sigma and that's 2 pi bonds. So the first option is incorrect. It's got 3 shared pairs of electrons. It is 3 shared pairs of electrons. That there are 3 bonds. Sigma bond, that's 2 electrons being shared. Pi bond, that's 2 electrons being shared, and the 2 pi bonds. So the second statement is correct. And it's got 2 lone pairs. It does have 2 lone pairs. Like if you have 2 nitrogen atoms and they end up sharing electrons, like they have a triple bond in the middle. Now nitrogen is in group 5, so it shares 3, so there are 2 electrons remaining. This one also has 2 electrons remaining. So that's your lone pair. That's one lone pair, and that's another lone pair. So it's got 2 lone pairs. Lone pairs are orbitals or electrons in the outer shell that are not involved in bonding because their orbitals are full. For example, if you look at the electronic configuration of nitrogen, it's got 1 lone pair. It's got 1 orbital that will not be involved in bonding. This one over here. The reason it's not going to be involved in bonding is that it's completely full. It doesn't have any room to keep someone else's electrons. So only 3 of the orbitals would be bonding. They would be forming 3 bonds. Now, the next one is, you're supposed to count how many sigma bonds are present in this molecule. Remember, the first bond between atoms is a sigma bond. So you would have to, what I'm going to do is I'm going to rub off the hydrogens, and I'm going to draw all the hydrogen atoms. So, I mean, this carbon will have 2 hydrogens. This one will have just 1 hydrogen. This one will have 2 hydrogens. Then I have CH2, so that's 2 hydrogens. This one will have 1 hydrogen, and this one will have 2 hydrogens. So you're supposed to count the number of sigma bonds, or every bond has 1 sigma bond. So that's 1, 2. A double bond has 1 sigma plus 1 pi. So we can ignore the pi. We're counting the sigma bond. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's 9. You've got 10, 11, 12, 13, 14, 15. This is 16, 17, and 18. So that's a total of 18 sigma bonds. Just remember that the double bond has just 1 sigma bond. The other one is a pi bond. Is this question clear?
Yes, sir.
Rubab, Zahib, is this clear? Zahir, is this clear?
Yes, sir.
Yes, sir.
So the next one, it's about ethene again. So you're saying it consists of one sigma and one pi bond, which orbitals overlap to form each of these bonds. So I told you that we just drew this somewhere. So let's draw this again. Remember, when carbon is bonded to 3 atoms, that means it is sp2 hybridized. What that means is, whenever you see a carbon atom that's bonded to just 3 atoms, which is the case in ethene, carbon has 4 electrons. That means 3 of its electrons got pulled in different directions. There is no 4th atom, so the fourth electron or orbital remained unchanged. So out of the 4 electrons, 3 of them, they changed shapes. They became sp2 hybrid orbitals. We went over this in detail. Carbon is only bonded to 3 atoms. 1 electron went this way, 1 electron went that way, 1 electron went this way. So if we have a look at hybridization, so sp2 hybridization was, just a quick recap. Remember, carbon had 4 electrons in its outer shell. There was 1 electron buzzing in a spherical region, 1 on the x-axis, 1 on the y-axis, 1 on the z-axis. It's got 4 orbitals. When carbon is bonded to 4 atoms, the electrons get pulled in 4 different directions. 1 gets pulled over here, 1 gets pulled over here. So that is sp3 hybridization. That means all the 4 orbitals, they've changed shape. I mean, you still have 4 orbitals, but they have a different shape now. And you call them sp3 hybrid orbitals. So instead of having an s orbital, which was spherical, now you have an sp3 orbital, which is not spherical. So carbon is tetrahedral when it's bonded to 4 atoms, and the hybridization is sp3. The second one that we did was when carbon is bonded to just 3 atoms. That means 3 of its orbitals, 3 of its electrons, they got pulled in different directions, like a fan. 1 went here, 1 went here, and 1 went here. The 4th electron, no one initially attracted it. So carbon has sp2 orbitals overlapping over here. It's got a sp2 hybrid orbital that's overlapping over here, and it's got an sp2 hybrid orbital that's overlapping over here. And then there is this unchanged p orbital. This unchanged p orbital would then start forming a pi bond with the unchanged p orbital of the other carbon atom, which is also sp2 hybridized. It's got 3 electrons getting pulled in different directions. The 4th electron is still in its orbital. So they start overlapping and they end up forming a pi bond. So in this question, they're asking who ends up forming the sigma bond. So it's basically sp2 and sp2 hybrid orbitals that are combining together. I mean, the other carbon atom, it's again sp2 hybrid orbitals. So an sp2 hybrid orbital of this carbon, an electron of this carbon would overlap with an electron of this carbon atom, and they would end up forming a bond in the middle. And who ends up forming the pi bond? It's the unchanged 4th electron, which is the p orbital. They would then overlap above and below. So it's a p and p overlap. So the first option is going to be correct. Okay, remember, I mean, this is something that you have to remember specifically about carbon atom, that when carbon is bonded to 3 atoms, it's got 4 electrons. So the 3 electrons are now in sp2 hybrid orbitals. The 4th one is still in its original orbital, which is the p orbital. And if it bonds with another carbon atom having the same hybridization, then these two overlap. So an sp2 hybrid orbital overlaps with the sp2 hybrid orbital. The pi bond is formed when the unchanged p orbital overlap together. So it's a p and p overlap. Is this also clear? Rubab,
Yes,
Hania,
sir.
is this clear? Zari, is this clear? Mariam?
Yes, sir.
So now, the next one is which molecule contains a nitrogen atom with sp hybridization. So with sp hybridized orbitals. So for an sp hybridized orbital, remember, what did we study about sp hybridization? We studied this thing. Where's our sp hybridization? Just a second. This was sp hybridization. sp hybridization happened when carbon, remember carbon had 4 electrons in 4 different orbitals. Carbon was only bonding to two atoms, like in carbon dioxide or in HCN. Whenever carbon is bonded to 2 atoms, that's sp hybridization. What happens in that case is that focus on the carbon in the middle. 1 electron gets pulled in this direction, bonds with nitrogen. 1 electron gets pulled in this direction, bonds with the hydrogen atom. So those are your sp hybrid orbitals because they got pulled in different directions. So that now their shape has changed. So you give them new names. Instead of calling them spherical or dumbbell shaped, you start calling them sp hybrid orbitals. So you've got a carbon atom. Remember, it has 4 electrons in 4 different places. 1 electron gets pulled towards the nitrogen atom, 1 electron gets pulled towards the hydrogen atom. So that means 2 electrons are now busy. These 2 electrons are gone. They've bonded, and they're called sp hybrid orbitals because the shape is now different. They got pulled over here. This one got pulled over here. Carbon still has 2 spare orbitals, one on the y-axis, one on the z-axis. So let's think of the blue one as being on the y-axis and the red one as being on the z-axis. These 2 spare orbitals, they end up forming 2 pi bonds because the neighboring nitrogen atom also has 2 spare orbitals. It's got a total of 3 spare orbitals that needed filling up. It got one of its electrons from the sp hybrid orbital. It pulled its electron, so this orbital is already full. So nitrogen did receive an electron already. So the 2px is already full. The 2py and 2pz are left. So the 2py and the 2pz are still left. So the remaining orbitals would start overlapping above and below. The red ones would be in front and behind. So this is sp hybridization. Just remember, when carbon is just bonded to 2 atoms, 2 of its orbitals would change shape. The other 2 would remain as they were, which you can see over here. 2 of the electrons went in different directions, where the remaining 2 orbitals, they maintained their shape and they ended up forming pi bonds. So in this question, it's saying which molecule would be sp hybridized. It's going to be when it's bonded to 2 atoms. That's when it's going to be sp hybridized. So if you go back to the question, it's going to be HCN. We were talking about HCN, and HCN, it is bonded to 2 atoms. So that is going to be your sp hybridization. Okay? Is this clear, sp hybridization?
Yes, sir.
Zari, is this clear? Rubab, clear?
Yes, sir.
Now shapes of molecules. So we've got ammonia and ammonium ions. Okay? So I'm just going to talk about ammonia. Ammonia is NH3. So it's going to look like this. Now, shapes of molecules. Ammonia has, or nitrogen, remember the shape of the molecule is determined by the central atom. So over here, you've got a nitrogen atom and it's bonded to 3 hydrogen atoms. So if you have a look at the shapes that we did. So shapes of molecules. So I told you that when you have 4 pairs of electrons or 4 bonds around the atom, that's tetrahedral. And sometimes you have a lone pair plus 3 bonded pairs. So it's still 4 pairs of electrons. There's a bond over here, electrons over here, and a pair of electron over here. But this electron is not bonded to anything. So I told you that it's the same tetrahedral shape, except that the top is missing. There's nothing attached on the lone pairs. You still have electrons there, but they're not bonded to anything. So it's exactly the same shape, except that there's nothing on the top. So it's like a pyramid. It's a nitrogen atom that's sitting on top of a pyramid, and the angle is 107. I told you that the shape is derived from a tetrahedral shape, except that the lone pairs have a slightly greater repulsion, which is why the angles become slightly smaller. So this one is 107 degrees, and it's going to be tetrahedral. Not tetrahedral, pyramidal. So ammonia molecule is going to be pyramidal. And the ammonium ion has 4 bonds. So that would be proper tetrahedral. It's going to be, it has 4 bonds because it's got a lone pair, and there's an H+1 that's sticking to those or attracted to those lone pairs. So that's a proper tetrahedral shape, because now you've got 4 different directions. So that's going to be regular tetrahedral. And what about the bonds present? Now, in both ammonium NH4+1 and NH3, there is no double bond. So that means the only bonds that are present are sigma bonds, because pi bonds are only present when there is a double bond. So the option for this one is going to be A. Okay, Alicia, is this clear? Aisha, is this clear? Anna, clear?
Sir, could you repeat that?
Yes, sir.
I'm just saying all of them are single bonds, right? So whenever you have a single bond, that's by default a sigma bond. Is that clear?
Yes.
Okay, this is what we learned. The first bond that's always formed between atoms when we are doing sigma and pi bonds, the first bond, the electron density is always in the middle. So that's always a sigma. If there are other bonds forming, they would be pi. The electrons would be overlapping above and below. So they would be pi. So whenever there's a single bond, that's always a sigma bond. You get pi bonds when there's a double bond, when there's a triple bond. That's when you get pi bonds. So next one, what is always involved in a carbon-carbon pi bond? A pi bond is a shared pair of electrons. That's true. It's always a sideways overlap of orbital. That's also true. Like in ethene, carbon is fan-shaped, sp2 hybridized. And the orbitals, the spare orbitals, they start overlapping above and below. So it is a sideways overlap of orbital. That's also true. And the last one is that it always has delocalized electrons, which is not true. The electrons are not delocalized. Electrons are right over here. Delocalized means that they're free to move anywhere they like. So it's not delocalized electron. The electron density is kind of stuck in the middle between the two atoms. So that's not delocalized. So option number 3, whenever there's a bond, it's not delocalized. So this one as well, he's saying which one is a pi bond. So he's saying which one is a pi bond. So it's going to be B. That's a pi bond. They've drawn it differently, but it's just nucleus and the orbitals are going to overlap above and below. So they're showing the overlap in this way, that the two orbitals are kind of overlapping. So this one is the closest resemblance to our pi bond. Next is, which statement about covalent bonds are correct? A triple bond consists of pi bonds and 2 sigma bonds. We just did this. Whenever you have a triple bond, the first bond is a sigma, the electron density is right in the middle. The other 2 bonds are going to be pi bonds. Like in the nitrogen molecule, the first overlapping happened right in the middle. The other 2 bonds, pi bonds, were formed either overlapping above and below or in front or behind. So the answer to this one is going to be, the first one is incorrect. It's always 1 sigma bond, the rest are all pi bonds. So it's going to be 2 pi bonds. So the electron density in the sigma bond is highest along the axis between the 2 bonded atoms. That's correct. The sigma bond is always, the electron density is always along the axis between the 2 atoms, right in the middle of the 2 atoms. Like this is your sigma bond. So the electron density is right along the axis. The electrons can be found right in the middle. For pi bond, that's not true. Pi bond, the electron density lies above and below, not in the middle. Because the middle, when the pi bond is formed, the middle part is already occupied. And the pi bond restricts rotation about sigma bond. That is also true. I told you that I did write this over here, that when a pi bond is formed, you can't rotate this side independently, because this atom is now locked with the other atom. So this side cannot independently rotate. I did show you a video as well. So this atom cannot independently rotate now because its orbitals are now locked in place with the other atom's orbital. When there's a sigma bond only, the atom can rotate around. For example, where are sigma bonds? So for example, you've got a hydrogen atom. Rotation. I mean, this hydrogen atom over here can rotate. It doesn't really matter. The electrons are right in the middle. So the attraction of the nucleus and the electrons would still be there. So the two sides can rotate independently and the bond will not break. But when there's a pi bond formed, the rotation stops because the two atoms are now completely locked together. Like all the orbitals are overlapping. If this side starts to rotate, the pi bond over here would have to break. I mean, it can't rotate independently. That's not possible anymore. So independent rotation of the atom or its orbitals is not possible anymore. So that's not going to happen. Like over here, CNN, the bonds are kind of locked in place. So independent rotation is not possible. So the answer, a pi bond restricts rotation, that is also true. So again, this is just a repeat of the same question. We did a similar question. I think the answer was 18, so forget that as well. And so over here, I have to count the sigma and pi bonds. So just for clarity, what I'm going to do is I'm going to draw all the hydrogen atoms. So that's 3 hydrogen atoms. Remember, the first bond is always, that's 2 hydrogen atoms. And there are 2 hydrogen atoms over here. 3 hydrogen atoms over here. And there are 2. So the first bond, whether it's a single bond or double bond, that's always a sigma. So we can start counting. That's 1, 2, 3. This is the 4th one. Double bond will have 1 sigma. So that's 5, 6, 7, 8, 9. Then 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So the correct answer is going to be C. It's going to be D. And the pi bonds would be, there's going to be 1 pi bond here, 1 pi bond here, and 1 pi bond here. So that's going to be 3 as well. So that's the answer to this question. TK, Zaib, is this clear? Anna, is this clear? Mayim?
Yes, sir. Yes, sir.
So this one, which type of bond breaks and bond formation occurs in the addition polymerization of alkenes? So I'll just show you what addition polymerization is. You've got an ethene molecule. And then the double bond in the middle breaks. And the ethene molecules kind of connect with each other. And this thing continues to repeat. So which bond is breaking? The double bond changes into a single bond. So the pi bond goes missing. Like the first bond is always a sigma. So over here you have, in the middle, you've got 1 sigma and there is 1 pi bond. Now over here, you just have 1 sigma. So that means the pi bond is gone. So bond breaking, that's pi bond only. And which bonds are getting formed? There's single bonds getting formed over here and single bonds getting formed over here. So that as every single bond, that's a sigma bond. So it's going to be A. That's going to be our answer because the double bond goes away. So that means the pi bond goes away. And these extra bonds are formed, which are single bonds, and single bonds are always sigma. So bond formation that's happening is only sigma. That's a pair. Which elements have atoms? We did this question as well. So now let's start talking about geometry. And I'm only going to talk about angles. So this one is saying, okay, what are the angles of ethane and its combustion product? So ethane is C2H6. Can anyone tell me what is the bond angle or what is the shape when carbon is bonded to 4 atoms? Like look at the central atom. Carbon is bonded to 4 atoms. So it's making 4 bonds. Can anyone tell me what the shape is when carbon is bonded to 4 atoms?
tetrahedral.
Okay, so whenever carbon is bonded to 4 atoms, the shape is tetrahedral, which is this one. Okay, that's what your tetrahedral shape is. So the shape, the three-dimensional or the actual shape of the molecule is tetrahedral, and the angles are going to be 109 point. They're going to be 109.5. So what are the combustion products? The combustion products that are formed is carbon dioxide, which is CO2, and it's water. Now, they don't tell you about lone pairs. You have to figure out the lone pairs yourself. Focus on the middle carbon atom. Carbon never really has a lone pair because carbon has 4 electrons, so 2 got shared here. 2 of them got shared over here, so that's all the 4 electrons are busy. So there are no spare electrons. So carbon just has 2 bonds. When you have 2 bond pairs, there's a pair of electrons here and there's a pair of electrons over here. Whenever you have 2 bond pairs, the shape is this one. Whenever you have 2 bonding pairs, the shape is linear. They would repel each other and they would be as far away from each other as possible. So the angle would be 180 degrees. So one of them is 180 degrees. This one. It's going to be linear shape. Now water, oxygen, remember, has 6 electrons. So 1 bonded over here, 1 bonded over here. So that means there's a spare 4 electrons remaining. Or you can say that there are 2 lone pairs remaining. So in total, how many pairs of electrons do you got? You've got a bond pair of electrons over here. You've got a pair of electrons in this bond. You've got a lone pair and you've got a lone pair. So that's a total of 4 electron densities. So for 4 electron densities, we had this shape. The main shape was derived from the tetrahedral arrangement when you have 4 pairs of electrons around the atom. So the shape is tetrahedral, except that on 2 sides, you've got lone pairs. On 2 sides, you got atoms bonded to it, but on 2 sides, there is nothing attached, except that they are lone pairs. So the lone pairs will not be counted in shape because there's nothing attached on that side. So the shape is going to be considered bent. It's just V-shaped. I mean, they call it V-shaped as well. It's non-linear. And because of the extra lone pair repulsion, the bonds would be slightly closer together. So instead of being 109.5, the angle would be 104.5 degrees. So 2 bonded pairs and 2 lone pairs, the shape is 104.5. So the correct answer would be this one. Over here, it's 104.5, and on the top, it's 180 degrees. Okay. Is this clear? Hani, is this clear?
Yes.
Okay. So as the next one, in which molecules do all the carbon atoms lie in the same plane? So this one is a slightly tricky question. I'll draw the molecules. The molecules are butene means and 2,3-dimethyl. So there's a carbon here and there's a carbon here. I'm not drawing all the other atoms because he's only talking about the carbon atoms. So forget all the other atoms. It's an incomplete structure, but I've only drawn the carbon atoms. So what's the arrangement around this carbon atom? It's got how many bond pairs? It's got a pair of electrons over here, a bunch of electrons over here, and over here, and over here. So that's 3 pairs of electrons. So when you have 3 pairs of electrons, the shape is going to be trigonal planar. Whenever you've got 3 pairs of electrons, it's going to be fan-shaped. So carbon over here, this carbon over here, it's going to look like this. It's going to be fan-shaped, double bond. The other carbon atoms would be. And then, I mean, this carbon atom over here would also be fan-shaped. It's got 3 bonded pairs of electrons. So it's like 2 fans connected to each other, and the angle would be 120 degrees. Fan is a planar molecule. A fan is a 2-dimensional molecule. It just has 2 dimensions. So the angle would be 120 degrees, and it's going to be planar. So the atoms would lie in the same plane. It would be completely flat, just like the blades of the fan. They would be all lying in the same plane. So that's true. So what about propane? Is the first one clear?
Yes, sir.
So the next one is, the next one is propane. Let's talk about propane. You've got, in propane, you've got 3 carbon atoms, but all of them are making single bonds. So that is what propane is. But remember, he's only talking about the carbon atom. So forget all the hydrogen atoms. I'm just going to rub them off. I don't care about the hydrogen atoms. The question is only about the carbon atoms. So let's just focus on the central atom. That's going to determine the shape of the molecule. So over here, you've got this carbon atom, and the central carbon atom is bonded to 4 atoms. So when it's bonded to 4 atoms, that means it's going to be tetrahedral. So that means one bond would be out of the page and one would be going into the page. So it's got, this carbon atom has 2 hydrogen atoms bonded to it. So there's one H and there's another H. And it's got 2 carbon atoms bonded to it as well. Now remember, in a tetrahedral shape, 2 of the bonds lie in the same plane. Like this bond and this bond, they lie in the same plane. One of the bond is coming towards you and one of them is going behind you. So 2 of the bonds are not in the plane. They're either into the board or they are out of the board. You can see the shape of a tetrahedral molecule. This one. So if you look carefully, then this is partially planar. Like this bond and this bond, they lie in the same plane. This bond over here that you can see, that's actually pointing towards you. So it's coming out of the board. And this other bond that's going behind you, that's going into the board. So these 2 are not lying in the same plane, but these 2 bonds are lying in the same plane. So the structure is partially planar, while these 2 are not planar. Is this point clear?
Yes, sir.
Okay, Rubab, is this clear? Bayam, Abdullah, is this clear?
Yes, sir.
Yes, sir.
Okay, so these 2 bonds are planar. They lie in the same plane. This one is coming towards you. This one is going into the board. So that makes it 3-dimensional. But this structure is planar. So he was talking about in the question, he was talking about the carbon atoms only. So ignore the H atoms. The H atoms are not planar. That's a tetrahedral shape. Focus on just the carbon atoms. The carbon atoms can be planar. They can exist in the same plane. One of the H would be pointing towards you. One of the H would be going into the board. So even in the tetrahedral shape, the carbon atoms can lie in the same plane. So the first one is correct and the second one is also correct. And the last one is cyclohexane. Can that be planar? Now cyclohexane is 6 carbon atoms in a cyclic structure, and each one has H atoms attached to it. So each carbon atom is tetrahedral. It's got, if you focus on each carbon atom, then it's tetrahedral. Now it would be impossible that this structure is planar. We did study that in a tetrahedral shape, 2 of the bonds are planar. But if you're connecting so many tetrahedral carbon atoms together, then it's impossible for them to be actually planar or for them to exist in the same plane. That is going to be impossible. That they lie in the same plane. The hexane molecule is, I can show you the shape of a hexane molecule. Just 1 second. So cyclohexane is like connecting lots of tetrahedral arrangements together. So probably this one would be good enough. Just a second. So this one. I mean, this is a tetrahedral. This one is tetrahedral. This is tetrahedral as well. This is tetrahedral. All the angles are 109.5. So if it's cyclic, it would be kind of impossible for them to all exist in the same plane. That would be for the carbon atoms to exist in the same plane. I mean, there was an even better shape. Just a second. I mean, this one. So you can see the shape of this molecule. That's a cyclic structure. Tetrahedral, another tetrahedral, all the carbon atoms are tetrahedral. So it's not planar, it's not flat. Okay, planar means it's going to be a completely flat molecule. The carbon atoms cannot exist in a completely flat arrangement because the tetrahedral shape is by default not planar. So you can have a simple tetrahedral could have two bonds that could be planar, but if you've got so many tetrahedral structures connected to each other, then it would be impossible to keep all the carbon atoms in the same plane. Okay, is this point clear?
Yes, sir.
Okay. Let's continue tomorrow then with some more past paper questions. Okay, okay everyone.
Thank you,
Allah
sir.
Hafiz.
Take care.
Allah
Love
Hafiz.
Love
Hafiz.